Stand under the night sky on a clear, cold evening, and the universe will seduce you. Stars pinprick the darkness in familiar constellations. Jupiter's moons march in perfect order. Galaxies spiral like frozen fireworks. It is beauty on the grandest possible scale. But beauty in nature is more than just what the eye can see. In the subatomic world, the same patterns repeat: symmetries, proportions, harmonies. Beauty is not simply decoration, but structure, a language written deep into the laws of reality. Indeed, again and again, our study of physics has confirmed this. Newton found a single equation to explain both the fall of an apple and the orbit of the moon. Einstein's equations bent space and time themselves. And yet, the history of science is also littered with failed, beautiful theories. For beauty alone is not enough. A successful theory must survive its trial in nature's courtroom. And now, at the center of that courtroom, stands string theory. String theory is arguably the most audacious and seductive vision physicists have ever produced. The remarkable suggestion that all particles and forces in the universe are nothing more than the vibrations of tiny strings. Gravity, electromagnetism, quantum mechanics, even time itself. All could be woven together by a single thread. A final theory, the ultimate unification. A glorious hymn to symmetry and elegance. But there's a catch. For unlike Newton's gravity or Einstein's curvature, string theory is still on trial. For almost 60 years, it has resisted every attempt at empirical confirmation. Each time experimenters cornered it, the theory has adapted, reformed, and survived. And so string theory finds itself in the dock. On one side, the defense, invoking beauty as their alibi. On the other, the prosecution, demanding hard evidence. Every triumph will be cross-examined, every failure entered into the record. Witnesses will testify, some for string theory, others against it. And finally, the jury will weigh the evidence in pursuit of a verdict. Is string theory a glimpse of the ultimate truth, or is it a beautiful illusion destined to be remembered as physics' most seductive false promise? The courtroom is now in session. In the early 1990s, American physicist Paul Ginsburg revolutionized how cutting-edge research was shared and reviewed. He created Archive, which allowed preprint papers to be transferred over the internet, even though the World Wide Web didn't even exist yet. Transferring millions of articles digitally, it has since been hailed as one of the 10 computer codes that transformed science. Of course now, printing and mailing copies for review seems a rather archaic concept, just as booking a medical appointment on the phone might be if our sponsor today, ZocDoc, have anything to do with it. Getting hold of a doctor can be frustrating, from the calling around, to the phone tag, to the waiting on hold. But ZocDoc can remove all of this wasted time. The website lets you search and compare local in-network doctors, instantly see available appointment times, and even book them right there within ZocDoc. Indeed, there are more than 150,000 providers within more than 200 specialties across all 50 states, with real doctor profiles and lots of reviews from patients. You can quickly find someone that's well reviewed, takes your insurance, and just book without having to call anyone. Usually you can grab appointments within 24 to 72 hours, and same-day appointments are sometimes available too, and all of this is totally free to use. So, to prioritize your health without the fuss, go to my link in the description and get that appointment off your to-do list. We have to remember that what we observe is not nature itself, but nature exposed to our method of questioning. Flames leap from the stovetop. Knives flash, pans hiss and simmer. Somewhere behind a wall, a chef is cooking. But you can see none of this. All you have is a hatch in the wall. From one side, you can see a tray of ingredients: lamb, garlic, turmeric. Later, a finished plate is pushed back out. But you never glimpse inside the kitchen. You never hear the chef. You simply see what went in and what came out. So you start paying attention. When you provide chili, coconut, and lime, the same dish always returns. Swap the lime for tamarind and something entirely different emerges. Over time, the patterns become clear. The recipes may stay hidden, but the correlations don't. Eventually, you stop asking how the food is made. You just learn the rules. Input, output. This was the situation facing particle physicists in the late 1960s. Only their ingredients were colliding particles, and the resulting dishes were sprays of stranger, more exotic particles. But the recipe, the thing that told them how one became the other, remained completely inaccessible. And nowhere was this more vividly embodied than in California, a place where two very different revolutions were unfolding. The air is thick with incense and rebellion. Long-haired teenagers dance barefoot in Golden Gate Park, preaching peace and rejecting the establishment. Jefferson Airplane, Janis Joplin, and Jimi Hendrix blare from nearby speakers as 100,000 hippies descend on San Francisco to turn on, tune in, and drop out. It is 1967, the summer of love, and couldn't be more different from the sterile scene unfolding high up on a hillside just across the bay. For there, physicists, clad in starched shirts, ties, and elbow patches, hover over dusty chalkboards and computer printouts. And yet, arguably, the hippies and the physicists have more in common than it first appears. For in their own ways, both are seeking a higher truth. One through free love and LSD, the other through fast-moving protons and liquid hydrogen. By the late 1960s, the Bevatron at the Lawrence Berkeley National Laboratory in California ranked among the world's most advanced particle accelerators. The Bevatron was a proton synchrotron. Within this type of accelerator, physicists speed protons up to nearly the speed of light before aiming them at a tank of liquid hydrogen held just below boiling point. The protons rip through the hydrogen like machine gun fire. New particles ricochet into existence, children of the carefully instigated collisions. The physicists have cleverly set all this up inside a magnetic field, which cajoles the charged particles into curved paths, the exact shape of which betrays the mass and charge of their creators, with millions of photographic plates capturing this intricate dance as particles pirouette like ice skaters, this way and that. Thanks to experiments like these, the number of new subatomic particles exploded as the 1960s drew to a close. But when physicists tried to use their existing quantum rulebook to predict the trajectories of these new particles, they failed miserably. Whatever was happening at the point of collision, they were missing something fundamental. However hard they tried, they couldn't glimpse within the particle kitchen. So instead, they were reduced to focusing on results, not process. Eventually, they turned to a pragmatic workaround called scattering matrix or S-matrix theory. This method sidestepped the messy details of what actually happened during the collision and, like the chef's hatch in the kitchen wall, focused only on matching inputs with outputs. For example, the more energy physicists fed into their collisions, the bigger the portion sizes that came back. But still, the recipe itself stayed firmly locked behind the wall. That was until 1968, when a young physicist working in relative obscurity found a key to unlocking these subatomic secrets: Gabriele Veneziano. Veneziano was born in Florence in 1942. A shy but technically gifted student, Veneziano had moved to Israel to complete his PhD, before taking up a research position at CERN, near the Swiss city of Geneva. Although widely respected, CERN had yet to become the particle physics powerhouse that it is today. And it would be at CERN, in a small office, that Veneziano stumbled across a formula originally discovered by Swiss mathematician Leonhard Euler. Known as the Euler beta equation, Veneziano plucked it from the annals of 18th century mathematics and applied it to 20th century particle physics. It was as if he'd stumbled across the chef's secret menu, the guide that, for the first time, revealed exactly how the portion sizes scaled with the ingredients. What input matched what output. Veneziano published his paper and then headed off on a 4-week vacation, and in his own words, did not think much about it. But by the time he returned, his formula had already become the talk of the town. And it would be this formula that would turn out to be the founding discovery of string theory. To the defense, this was beauty in its rawest form. A centuries-old equation traced perfectly over brand-new data. Veneziano's equation would become the first exhibit in what would grow into one of the longest-running trials in theoretical physics. Although at the time, no one realized it. Indeed, as Veneziano later admitted, I was just looking for a model. I had no idea it would lead to strings. And so armed with Veneziano's equation, physicists could finally match the inputs to the outputs. It was a persuasive piece of evidence, but circumstantial. There was still no closer to describing what exactly was actually occurring at the point of collision. They could still not see inside the kitchen, understand why or how all these new particles were created. The answer to this, however, came sooner than expected, for in September 1969, mere weeks after the hippie movement reached its cultural crescendo at Woodstock, a radical reinterpretation of Veneziano's idea would come in part from physicist Leonard Susskind, a witness for the defense of string theory we will meet many, many times. Susskind was born in the New York borough of the Bronx in 1940, a cultural world away from hippie California. His father was a local plumber working the rotten tenements in and around Harlem. And after attending college to study heating engineering, Susskind Jr. fell in love with an unlikely muse: theoretical physics. Eventually, he plucked up the courage to tell his father that he wanted to be a physicist. "Get out of here, you ain't gonna work in no drugstore," came the reply. "Not a pharmacist, a physicist, like Einstein," Susskind Jr. had clarified. At the end of the 1960s, Susskind hit upon a new interpretation of Veneziano's work. In Chicago, the same truth was dawning on Japanese physicist Yuichiro Nambu, and Danish physicist Holger Bech Nielsen also independently had the same lightbulb moment. The trio each realized that the root cause of physicists' problems with colliding protons was that they'd been treating them as point-like particles. Infinitesimally small specks with no dimensions, much as we still think of electrons today. Nambu, Nielsen, and Susskind suspected a deeper truth was hiding behind Veneziano's equation. Protons weren't point-like, they proposed. They were strings. One-dimensional ropes that could vibrate in different ways. Rejection was swift. Reviewers dismissed it, and the dismissal cut deep. Boom! I felt like I'd gotten hit over the head with a trash can. I was very, very deeply upset, Susskind would later recall. According to the new hadronic string theory they had proposed, the mysterious escalating melody of masses inside the Bevatron wasn't a collection of completely different particles, but instead came from the same string vibrating at different frequencies. Was this the chef's secret recipe? Was nature cooking with strings? For a brief moment, physicists, just like the hippies, had elevated themselves to a state of deep enlightenment. The trouble is, they were wrong. This unsettling realization came on the back of an experiment taking place less than an hour's drive south of Golden Gate Park, at a completely different type of accelerator to the Bevatron, the Stanford Linear Accelerator Center. Here, physicists weren't firing protons, they were using them for target practice. The accelerator center was effectively a high-speed gun, shooting electrons down a 2-mile-long range. The hope was that by relentlessly bombarding protons, physicists could finally see what they were made of. The Bevatron was like a butterfly net, hoping to catch whichever strange subatomic creatures fluttered past. The Stanford Linear Accelerator Center was more like a surgical scalpel, slicing open the proton to see what was inside. If protons were large clouds of charge, as had been the assumption, then the incoming electrons shouldn't lose a lot of energy upon collision with their tiny targets and would be scattered off at shallow angles. Except that's not what physicists saw at the accelerator center. Instead, electrons lost significant energy and pinged off at surprisingly large angles. It was as if the electrons were hitting hard substructures within the proton itself. The idea had already been floating around in the physics ether for half a decade. In 1964, physicists Murray Gell-Mann and George Zweig had proposed that some particles were in turn made of smaller particles, quarks. Some models worked better with them, but until the experiments at the Stanford Linear Accelerator Center, it wasn't clear whether quarks were real or mere mathematical sleights of hand. But it wouldn't take long for physicists to tie the loose ends together. Within a few years, the proton's structure had been neatly bundled into a theory called quantum chromodynamics, or QCD. This theory perfectly explained how protons are made of 3 quarks, bound together by the exchange of particles called gluons. And so the electrons at the Stanford Linear Accelerator Center were pinging off the quarks inside the protons. Quarks and quantum chromodynamics were a hammer blow for the infant idea of string theory. In courtroom terms, it was as if the prosecution had landed a devastating cross-examination. The case for string theory had barely been opened, but now it seemed to slam firmly shut. Most physicists quietly left the field behind and moved on to other projects. Only a few hardy souls remained, leaving string theory lifeless, but not completely dead. But those who stayed behind started asking a different question. What if string theory wasn't just a failed detour in particle physics, but the first clue in a far deeper mystery? Not just a theory of the subatomic, but a theory of everything. String theory is a part of 21st century physics that fell by accident into the 20th century. A pipe rests gently on a scattered pile of dog-eared papers. Books jut out precariously from the edge of the table. A single piece of chalk lies expectantly on a ledge beneath a blackboard filled with frantically written equations. After Albert Einstein died in April 1955, this was the state of his office, and it was a scene we were never supposed to see. When Life magazine photographer Ralph Morse heard of the physicist's death, he raced the 90 miles from his home to Princeton, and after bribing his way in with a bottle of scotch, Morse was able to photograph Einstein's desk within hours of his death. But it's what's on the blackboard that's perhaps the most telling. This was Einstein's final attempt to solve a problem that had become a decades-long obsession. Einstein was searching for a unified field theory, a single framework that could explain both gravity and the electromagnetic force. And yet, despite 30 years of trying, his holy grail remained agonizingly out of reach. Someone else would have to step forward, reopen the case, and find what even the great man could not. By the time string theory appeared at the end of the 1960s, physicists were attempting to do just that, to tie gravity to not only the electromagnetic force, but to the strong and weak forces too. One beautiful, elegant, and coherent theory of everything. The trouble was, gravity spoke a very different language to the other 3 fundamental forces. It is best described by Einstein's own general theory of relativity, and introduces the smooth, continuous fabric of space-time, a fabric that is warped by objects with mass to provide the illusion of an invisible gravitational pull. In quantum physics, on the other hand, the language of the other three fundamental forces, electromagnetism and the strong and weak force, this smoothness is jarred. In the quantum world, everything comes in blocks of fixed, preordained sizes. The universe it describes is grainy, the very opposite of that described by Einstein in his theory. These two worlds seemed unresolvably at odds. Remarkably, however, string theory, despite being bruised and battered by its run-in with quarks and quantum chromodynamics, offered a ray of hope, a faint glimmer of a theory of everything, a potential way to explain all four fundamental forces using the same language, the language of vibrating strings. Originally, physicists had only considered open strings, those where the ends were free to dangle like an ordinary piece of rope. A photon, for example, the particle that carries the electromagnetic force, is represented by a single vibrating string. The ends of the string represent charged particles. At one end is the electron, and at the other end is its antimatter partner, a particle called a positron. The photon string is literally the link between them, explaining the attraction between their opposing electric charges. When a particle meets its antimatter equivalent, they annihilate one another, with their combined masses turning into a flurry of energy. String theory therefore elegantly paints annihilation as the simple act of two string ends meeting. So far, so straightforward. But it was only when string theorists started exploring the properties of closed strings, those where the ends join together to form a continuous loop, that their jaws began to drop. And to understand the importance of closed strings to a theory of everything, we need to talk about a strange property of subatomic particles called spin. About a century ago, physicists realized that orbiting subatomic particles, like electrons, behave like they were generating two magnetic fields. Magnetic fields are created when electric charges move, so it followed that if the negatively charged electron has two magnetic fields, then it must be moving in two different ways. An obvious movement was the electron's orbital motion around the nucleus of an atom, but physicists wondered whether electrons could also be spinning on the spot. If true, electrons would be a bit like the Earth, which both spins on its axis and orbits around the Sun. However, physicists quickly realized their mistake. In order to generate that magnetic field, electrons would have to be spinning faster than the speed of light, and of course that would be impossible. So, while physicists no longer think of subatomic particles as actually spinning, they still use the word spin when it comes to describing the source of that second magnetic field, which turned out to simply be a property of the particle, not something caused by actual spinning. Different particles have different spin values, and that's what distinguishes the two families of particles from one another: fermions and bosons. Fermions, such as electrons, quarks and neutrinos, all have spins equal to a half. By contrast, bosons always have a spin that's equal to a whole number. The Higgs boson, for example, has a spin of 0. Other bosons are responsible for carrying the electromagnetic, weak and strong forces, and all of them have spins equal to 1. Yet according to string theory, the vibration of a closed string will always represent a particle with a spin equal to 2. And though it may not seem like it, this subtle realization was a landmark moment both in the storied history of string theory and in the entire history of physics itself. For the defense, this was Exhibit A. Long before string theory, physicists had speculated about a spin-2 particle. Now it appeared to fall naturally out of closed strings. The jury surely had to take notice. And so to hammer home their case, the defense called Soviet physicist Dmitry Blokhintsev to the stand. Blokhintsev was a big hitter in Soviet society. Indeed, he once wrote a book on the implications of quantum mechanics that aligned physics with Marxist-Leninist philosophy. It won him the Stalin Prize in 1952, and 4 years later he was made a hero of socialist labor. When Blokhintsev died in 1979, his obituary was signed by Soviet leader Leonid Brezhnev personally, who lamented that Soviet science has suffered a heavy loss. And it was in 1934, working alongside Fyodor Galperin, that Blokhintsev coined the word graviton to describe a hypothetical particle that would carry the gravitational force. The other three forces, electromagnetic, weak and strong, can all be neatly explained by the exchange of particles. These particles have been detected through experiments time and time again, like the photon for the electromagnetic force. However, no one has ever found a graviton. This is because the idea of a graviton has deeper problems. The other three forces and their bosons can all be explained by a set of rules known as a quantum field theory, a type of theory that physicists can use clever tricks to keep stable. With these other three forces, physicists can mathematically patch up any holes that appear in their theories using a trick called renormalization. Not so with gravity. Instead, patching one hole seems to create several more. Trying to patch those holes creates more still. In other words, a quantum field theory of gravity, one that contains gravitons, quickly breaks down at very high energies. Of course, this hasn't stopped physicists from working out just what properties a graviton should have. First of all, it has to be massless, just like the photon. The distance over which a force operates, its range, is linked to the mass of the bosons that carry it. The heavier the boson, the shorter the range. Gravity, just like the electromagnetic force, has an infinite range, and so gravitons must have a mass of 0. Gravity also affects all matter in the universe, regardless of other properties such as electrical charge. And it turns out the only way gravitons would be able to do this is if they are spin 2 particles. Indeed, this relationship is so sacrosanct that in fact any massless particle with a spin equal to 2 must behave like a graviton, and according to string theory, a closed string creates a spin 2 particle. On paper, that's a graviton. And it is here that we arrive at the single biggest attraction of string theory, the thing that has seen schools of scientists rally behind it, the reason billions of dollars have been poured into the field in the decades since, a key pillar of its courtroom defense, and the very idea that saw it resurrected from the dead. Without even trying, merely by considering what happens if a string forms a closed loop, suddenly one of the most sought-after particles in all of physics pops out of the theory. It was as if the witness had suddenly confessed before anyone had even posed the question, and, in the same breath, laid out the rest of the evidence. A single theory that would be able to predict the existence and properties of the bosons that carry all 4 fundamental forces, even gravity. And so, unsurprisingly, this version of string theory came to be known as bosonic string theory. This was physics at its most beautiful, and the defense argued that this inherent beauty strengthened the case for bosonic string theory even further. By treating the graviton as a closed string rather than a point-like particle, the holes in its quantum field theory suddenly could be patched, just like the other forces. There's no runaway chaos that obliterates the theory at high energies. And to understand this, let's imagine 2 masses inching ever closer to one another. Physicists describe gravity using an inverse square law. This means that every time you halve the distance between the masses, their gravitational attraction quadruples. As the 2 masses edge closer and closer together, the attraction between them skyrockets. And as the gap shrinks to 0, the strength of gravity becomes infinite, and the theory breaks down. But the gap can only shrink to 0 if the particles are treated as point-like, with no width, depth, or height. Bosonic string theory replaces this idea with particles as one-dimensional strings. And so if gravity works through the exchange of gravitons, and gravitons are closed strings that have a dimension, the 2 masses can no longer get infinitely close to one another and still be exchanging gravitons. With no runaway rampage towards infinity, physicists can patch the holes in the theory, just as they did with the other 3 forces. This was a prime example of beauty offering more than mere decoration. Instead, it offered salvation, the elegant geometry of strings vanquishing infinities in a way that point-like particles simply couldn't. The defense had seized the momentum with a simple, intoxicating idea. The apparent differences between gravity and its fellow forces could be explained away as the difference between a closed string and an open one. And at the heart of the matter, the forces were united by a single notion. Everything is vibrating strings. If bosonic string theory were correct, it seemed to offer something that even Einstein couldn't muster: a possible path to a theory of everything. The end of physics as we knew it, and the beginning of something far greater. And yet, if it were that straightforward, physicists wouldn't still be arguing over string theory to this day. There would be no need to put string theory on trial, no courtroom, no lawyers, and plenty of Nobel Prizes. Every trial begins with opening statements designed to dazzle. The defense had made its case with elegance and flair, but now came the cross-examination, and the prosecution's evidence was damning. In physics, as in art, symmetry is a key to beauty. A large crowd gathers around the tiny computer screen, eager to watch the drama unfold. Suddenly, the message arrives. It's clear, time-stamped and intact. But 3 minutes later, the physicist sends it. Something has clearly gone wrong, but not with the equipment, with reality. The message arrived before it was sent, its information travelling backwards in time, the usually ironclad rules of cause and effect upended entirely. This unnerving paradox is the kind of thing that happens when you introduce hypothetical particles called tachyons, particles that can travel faster than the speed of light. Tachyons were a fundamental flaw in bosonic string theory, which bizarrely seemed to predict their existence. For all its elegance and beauty, bosonic string theory seemed to summon the spectre of superluminal travel. The prosecution pounced. This was not beauty, but a grotesque gargoyle. Surely the correct theory of everything couldn't allow this. And yet tachyons were just the beginning. For faster-than-light particles turned out to be the least of string theory's problems. They were merely the first piece of evidence introduced by the prosecution in a long and seemingly watertight rebuttal. The speed of light as the ultimate cosmic limit is a cornerstone of Einstein's special relativity. And special relativity rests on an assumption so important that breaking it would be tantamount to physics perjury: Lorentz invariance. Lorentz invariance is the idea that the laws of physics don't play favourites. Whether you're drifting in space, sprinting down a corridor, or hurtling past the Earth at 99.9% the speed of light, the rules should remain unchanged. No observer can have a privileged view of reality. The speed of light is the same for all observers. And so strip away Lorentz invariance and reality starts to waver. Particles might behave differently depending on how fast you're moving. The whole of physics begins to crumble. In other words, Lorentz invariance seems non-negotiable. And yet when string theorists tried to apply quantum physics to their elegant strings, the algebra buckled. Lorentz invariance seemed to collapse. And that wasn't all. The prosecution pressed on. They reminded the jury that in quantum theory, particles can't take on just any value, only certain allowed ones. Yet when physicists tried to quantize bosonic strings, the math spat out phantom states with negative probabilities. Ghosts. Probabilities usually live on a scale from 0 to 1. 0 means impossible, 1 means certain. But bosonic string theory seemed to introduce probabilities below 0. And a negative probability isn't more impossible, it's nonsensical. Like betting on a horse with odds of -1, it just doesn't work. And so a theory that allows such absurdities is a theory in contempt of court. The prosecution had landed yet another hammer blow, but they weren't finished. They were going 3 for 3. For string theory also failed to reproduce a phenomenon already proven beyond reasonable doubt. Parity violation. The prosecution now called its star witness, Chen-Sheng Wu. Wu was born in the Chinese province of Jiangsu in 1912, mere weeks after the sinking of the Titanic. She'd stay in and listen to the radio instead of playing outside with other children. Her father would read her passages from scientific journals instead of children's stories. In 1936, she left China for the United States. It was a jarring transition. She looked into attending the University of Michigan, but women weren't even allowed to use the front entrance. The University of California, Berkeley, promised a more liberal life, yet Wu remained culturally adrift and far from home, often finding comfort in meals from a nearby Chinese restaurant. But scientifically, Wu flourished. She was recruited into the Manhattan Project and helped develop the atomic bomb. She later became known as the First Lady of Physics, and in some circles, the Chinese Marie Curie. But her most famous work came in 1956, when she performed a clever, intricate experiment to show that the weak force, the one responsible for radioactive decay, violates parity. To understand parity, imagine a clock reflected in a mirror. The numbers may be reversed, but the hands still go round in the usual direction from 12 to 3 to 6 to 9. The reflected clock behaves just like a clock in the real world, and so physicists would say that the two clocks exhibit parity. However, not all the fundamental forces behave this way, and it was Wu that proved it. Wu trapped spinning cobalt nuclei in a magnetic field and waited for some of the neutrons to decay into protons, emitting electrons in the process. The first time she ran the experiment, most of the electrons were emitted downwards. Look at this reflected in a mirror and you'd see the nuclei's spin direction reversed, just as the numbers on the clock were. But, like the hand on the clock, the direction of the emitted electrons would stay the same. And so Wu tested this reflection by flipping the orientation of the magnetic field, which sent the nuclei spinning in the opposite direction, just as in the mirror image. Except now, most of the electrons were spat out upwards. The mirror image did not match what we see in the real world, and so the weak force did not obey parity. Wu found that there was a left and right to fundamental physics. By the early 1970s, Wu's result wasn't in question. Parity violation had long been written into the rules of physics, proven time and time again. And yet once again, bosonic string theory, for all its elegance and potential as a theory of everything, simply couldn't account for it. It was yet another gaping hole in the defense's testimony. Here the contradiction at the heart of string theory was laid bare. Sometimes it wasn't beautiful enough, spawning hideous tachyons. Other times it was too beautiful, unable to accommodate the messy asymmetries of the real world, like parity violation. Beauty, it seemed, could cut both ways. Tachyons, impossible ghosts, no Lorentz invariance or parity violation, any one of these would be enough to consign a theory to the dustbin of history. And yet string theory, physics' perennial survivor, squirmed and wriggled its way out of all of them. Cornered and battered, the defense turned to an unlikely savior. English physicist Claude Lovelace. Lovelace was a paid-up member of the Eccentric Physicist Club. Known to be a bit of a loner, he would often avoid major conferences, yet still sent in important scientific papers. In later life, Lovelace filled his home with parakeets and thousands of classical music CDs. The unusual combination helped him think. Somehow, Lovelace had managed to become a physics professor without ever obtaining a PhD. He started one in London, but dropped out before completing it. That doesn't seem to have held him back. For in 1971, Lovelace made a fundamental, but often overlooked contribution to string theory. He argued that the universe has hidden dimensions, secret locked rooms the defense urged the jury to imagine, evidence concealed from view, but essential to their case. The world around us seems to be four-dimensional. There are the three spatial dimensions, left, right, up, down, front, back. Then the one dimension of time. In other words, we always need four numbers to accurately describe an object's location, 3 for where it is, and another 1 for when it is. However, Lovelace wondered what would happen if vibrating quantum strings didn't have to be confined to our four-dimensional world. And slowly but surely, he ramped up the number of dimensions. First 5, then 6, 7, 8, 9, eventually at a total of 26 dimensions, 25 space and 1 time. String theory seemed to stabilize. Others, including Holgerbeck-Nielsen, ran with the idea, proving that it both eliminated the probabilistic ghosts and maintained Lorentz invariance. Born in Copenhagen in 1941, Nielsen was another of physics eccentrics. The unkempt hair, the ever-present bow tie, and indeed back in the earliest days of string theory, it had been Nielsen who, alongside Nambo and Susskind, had realized that Veneziano's work implied strings. Unfiltered and unpredictable, perhaps Lovelace and Nielsen's maverick nature was just what was needed to open up the extra dimensions. String theory was suddenly on slightly stronger footing. The defense lawyers were regaining ground. But this newfound stability involved a massive trade-off, one that the prosecution will seize upon to undermine the case for string theory time and time again. In order to explain things we have a lot of evidence for, normal probabilities and Lorentz invariance, string theory would have to invent 22 additional dimensions that we have no evidence for. And even then, this sprawling, mega-dimensional reality can't solve all of string theory's problems. Time-travelling tachyons were still centre stage, and the lack of parity violation remained a gaping hole in the theory. But there were answers to be found there, too. The defence calls for its own star witness, Yuri Golfund. Golfund was born in 1922 in Kharkiv, which today is Ukraine's second-largest city. Even from an early age, he showed precocious talent. He started playing chess with his father aged just 4 and soon became the better player, underscoring the impact he would have, both on physics and the people around him. Fellow physicist and Nobel Peace Prize winner Andrei Sakharov once called Golfund a Mozart of physics. Picture a chessboard, like the one Golfund spent so much time playing on as a boy. A chessboard has 64 squares, divided equally between black and white. In other words, for every white square, there is a corresponding black square. In this way, a chessboard has an underlying symmetry. In 1971, Golfund became one of the first to propose that the subatomic world exhibits a similar kind of symmetry: supersymmetry. Just as every black square on a chessboard has a corresponding white square, so, suggested Golfund, every boson has a corresponding fermion, and vice versa. To name the supersymmetric partner of a fermion, you simply add an S before it. So, charmingly, the partner of a quark is a squark. An electron is paired with a selectron, and neutrinos are matched to sneutrinos. Indeed, later string theory pioneer John Schwartz once quipped that he wasn't responsible for this slanguage. However, the supersymmetric partners of bosons are named slightly differently, simply by adding an eno to the end. So the famous Higgs boson has a partner that sounds a little bit like a magician, the stupendous Higgsino. Though in practice, physicists often bend the rules, hence names like gluino for the fermionic partner of the gluon. Although to this day, no supersymmetric particles have yet been found, an absence that the prosecution will pounce upon later in the case. And so, at the start of the 1970s, several other physicists were also dabbling with similar ideas. Eventually, they combined supersymmetry with Lovelace's 26-dimensional version of bosonic string theory, and superstring theory was born. Initial results were promising. This new theory could now account for fermions as well as bosons. The inclusion of fermions could see off the parity issue, providing a way for it to be violated. It also did away with those pesky tachyons. No faster-than-light travel, no effect preceding cause. What's more, the number of spatial dimensions came crashing down, from Lovelace's unruly 25 to a slightly more manageable 9. And so, having been on the ropes for much of the prosecution's cross-examination, the defense team had rallied. For each of the major issues with the original bosonic string theory, superstring theory now provided an alibi. What had looked like a lost cause had yet again surged back to life. Beauty had become the compass once more, pointing towards a hidden country where string theory's problems seemed to dissolve into the mist. But that wasn't the end, for the prosecution were forced to pivot, honing in on a new line of attack, and not an unreasonable one. If these extra dimensions exist, why can't we see them? 6 extra dimensions that we had no evidence for were hardly more credible to the jury than 22. And so for string theory's case to remain stable, string theorists desperately needed an answer to a very basic question. If these extra dimensions really did exist, where were they? Why, you may ask, do the string theorists insist that space is 9-dimensional? Simply because string theory doesn't make sense in any other kind of space. Theodore Kaluza stands on the edge of the water, ready to prove a point. Now in his 30s, the polyglot theoretical physicist never learned to swim as a child. But who needs practice when you have books and theories? Kaluza has recently swatted up on how to swim in the pages of a manual, and upon entering the water, he duly swims at his first attempt. A triumph for the theoretical over the practical. Kaluza's mind was certainly a fertile one. He could speak at least 15 languages, and liked literature and philosophy almost as much as mathematics and physics. And like many physicists before and since, Kaluza became transfixed with the idea of unification. Just as medieval kings would try to unite their respective kingdoms through key and strategic marriages, physicists try to do the same with theories. Why have 2 different theories when a single, combined theory could suffice? Kaluza's big idea was to seek a matrimonial bond between Einstein's general theory of relativity and the rules of electromagnetism, a love match between gravity and light. The obstacle to such wedded bliss is that the mathematics of each of the theories is fundamentally incompatible with the other. As we've seen before, the equations explode in a fit of infinities. And yet in a 1921 paper, Kaluza was able to get them to gel under one condition: that the universe had 5 dimensions, one more than the 4 we are used to. Kaluza was clearly excited by the benefit of adding an extra dimension of space, writing in his paper that it could not amount to the mere alluring play of a capricious accident. And indeed, when he wrote to Einstein, the great man was more than encouraging. The idea of achieving this through a 5-dimensional world has never occurred to me, and is probably new. I like your idea immensely. But of course, as with any attempt to explain the world through extra dimensions, the fact that we don't experience more than 4 dimensions in our everyday lives was the proverbial elephant in the room. If Kaluza's extra dimension really did exist, where exactly was it? A potential answer would come from Swedish physicist Oskar Klein. The son of Stockholm's first rabbi, Klein became enchanted with science at an early age. Years later, he would recount the time when he borrowed his mother's opera glasses and used them to stare up at the stars. Working his way through school and university, Klein ended up studying chemistry before pivoting to physics, and independently to Kaluza, he came up with the idea of a 5-dimensional universe. However, this time offering up an explanation for why we don't see this mysterious 5th dimension. It is, Klein argued, curled up incredibly small. How small? On the order of the Planck length, the smallest meaningful distance in the universe. When we think of truly small things in physics, one of the first objects that comes to mind is the atom. Indeed, a typical atom is just 1/10 of a nanometer across. You'd need to line up 150 million atoms side by side in order to match the width of one of your fingernails. Small, but not small enough. For the Planck length is 16 trillion times smaller still. In fact, the Planck length is to the width of an atom what the width of an atom is to the size of the entire solar system. In the language of physicists, the extra dimension in Kaluza-Klein theory is compactified. In other words, it is so vanishingly small that we can't see it. And to see how this works in practice, imagine an ant crawling along the branch of a tree. From some distance away, the tree looks flat and two-dimensional, as if painted on some far-off canvas. But the ant knows the truth. There's a 3rd dimension, and safe in this knowledge, it can happily crawl around the circumference of the branch. In the same way, our universe would look 4-dimensional from up here on the scale of plants, people and planets, but there could be compactified, curled-up dimensions languishing in the hidden depths of reality. Despite receiving a warm reception from several towering figures at the time, Kaluza and Klein's insights were largely consigned to a mere footnote in the history of early 20th century physics. Until string theory once more summoned the spectre of hidden dimensions in the 1970s. By the start of the 1980s, superstring theory predicted the existence of no fewer than 6 extra spatial dimensions. The prosecution was circling. With the tachyon problem subdued and supersymmetry now on life support, string theory still had to answer for the 6 extra spatial dimensions that stubbornly refused to show themselves. The court was losing patience. If the defense had no credible explanation for where these hidden dimensions were hiding, the whole case might collapse. Enter the expert witnesses for the defense, Eugenio Calabi and Xingtung Yao. Just like Yuri Golfund, both Calabi and Yao had had their political troubles. Calabi was born into a Jewish family in Italy in 1923. The family was forced to flee when Calabi was just 15. Calabi eventually settled in the United States. Yao, however, had ended up stateless for more than a decade. He'd grown up in Hong Kong in the 1950s, but the British consulate removed his status in 1978 after he was granted US residency. However, he didn't gain US citizenship until 1990, and so when Yao won the prestigious Fields Medal in 1982, the mathematical equivalent of a Nobel Prize, he didn't hold a passport of any country. Yao's big breakthrough in the late 1970s was to build on the earlier work of Calabi to develop what are now known as Calabi-Yau manifolds. To understand the Calabi-Yau manifold, imagine you have a 9-dimensional piece of origami paper that represents space. Simple enough, sort of. Except you now have to fold it up so that it only looks 3-dimensional, matching the 3 spatial dimensions we experience day to day. But if you fold it haphazardly, your new 3-dimensional universe will have no supersymmetry, a key part of string theory. This means that the extra dimensions aren't some mere hidden inconvenience. They play a pivotal role in the shaping of our reality. They are the silent, invisible conductors of the great superstring orchestra. It turns out that only one incredibly ornate and intricate folding process works. One with all the creases perfectly aligned so that supersymmetry survives. And that final origami shape is the Calabi-Yau manifold. Even then, however, only some supersymmetry survives the folding process, not all. Just enough that it can still explain the particles we see in the subatomic world and the interactions between them. And so the folds of Calabi and Yau were undeniably beautiful. But the prosecution was suspicious. Was this physics, or mere mathematical stagecraft? And so it took a while for the abstract mathematical concept of Calabi-Yau manifolds to cross over into physics and reach string theorists. But by 1985, they had built it into their ideas. Once more, they'd taken a defibrillator to a dying theory. Superstring theory rose Lazarus-like, once again. The realization that Calabi-Yau manifolds could curl up the 6 extra dimensions while still preserving supersymmetry was a huge part of what is known today as the first superstring revolution. It granted string theory a stay of execution, a last-minute reprieve, but not a pardon. Indeed, the prosecution justifiably argued that such intricate and unobservable constructs amounted to little more than theoretical hearsay. Calabi-Yau manifolds weren't evidence. They were just an elegant alibi engineered to hide a lack of evidence. String theory was still very much on trial, and the stakes were rising. And so the courtroom buzzed as 2 more key witnesses prepared to testify: Michael Green and John Schwartz. Imagine that the universe is a smartphone, and that a theory of everything, like string theory, represents the phone's operating system. It powers the phone's key processes, ensuring they all run smoothly. In the early 1980s, the string theory operating system kept producing anomalies in the universe, deep bugs in the code that would make the apps crash and the clocks skip. Clearly, any theory of everything worth its salt had to be more stable, much more stable. And so in 1984, Green and Schwartz invented the equivalent of a software patch. Known as the Green-Schwartz mechanism, it deployed a sort of diagnostic tool into the code that could identify and fix bugs in real time. And at a stroke, superstring theory was stable. In a sense, beauty had been called to the stand again, but not the soaring elegance of symmetry this time, but the precise economy of a patch that saved the theory from collapse. To the defense, it showed resilience and adaptability under pressure, but to the prosecution, it was but a bandage over a deeper wound, a clever fix masking fragility. But of course, the case for and against string theory is never straightforward. It's arguably the most complex trial physics has ever faced, which is exactly what makes arriving at a verdict such a gargantuan and intimidating task. And indeed, under cross-examination, the prosecution found a hole in Green and Schwartz's testimony. In order for the bugs to be fixed, and for the resulting strings to still carry charges and interact with one another, only certain symmetries were allowed. Even more careful and specific folds in the intricate origami of the universe. And there was an even bigger problem. Suddenly, there wasn't just one coherent superstring theory that worked, there were 3. Which one, if any, represented the true operating system of the universe? String theorists were about to sink deeper into the quagmire. At the beginning of the 1970s, after quarks had put the original string theory to the sword, there had been a massive exodus of researchers from the field. The number of people working on string theory had dwindled to a handful, toiling away on the fringes of physics. But the combination of the Green-Schwartz mechanism and the Calabi-Yau manifolds ushered in the first superstring revolution, convincing many that string theory was viable once again, and so a tsunami of new physicists joined the fray. And among them were 4 physicists from Princeton University: David Gross, Jeffrey Harvey, Emil Martinek, and Ryan Rohm. They quickly became known as the Princeton String Quartet. Together, they worked on the idea of heterotic strings. A heterotic string is a chimera. It is a hybrid of a superstring and the original bosonic string. The Princeton String Quartet realized that there were 2 different heterotic superstring theories that could also run like the universe's operating system without bugs, still yielding the necessary supersymmetry and summoning all the particles and forces to boot. And those 2 theories, to the 3 that Green and Schwartz had discovered, and there was no longer a single superstring theory, but a total of 5 possible superstring theories. Any one of them could be the long sought after theory of everything, or none of them. And so, let's summarize the case so far. String theory started out simple. Particles were vibrating strings, not point-like. But abominations like tachyons entered the fray, and suddenly the universe needed to have 22 extra dimensions of space. First, supersymmetry was required to vanquish the tachyons, but this proceeded to predict the existence of a whole range of particles that still no one has ever seen. Although supersymmetry did manage to reduce the number of extra spatial dimensions from 22 to 6, but these still needed to, rather conveniently, be curled up so small that they remain out of sight. And the only way to actually curl them up and preserve supersymmetry was by following the elaborate folds prescribed by Calabi and Yau. Even then, only a watered-down version of supersymmetry remained, a diluted superstring theory that was unstable unless patched by the Green-Schwarz mechanism, and that created 5 possible superstring theories instead of 1. The courtroom was drowning in contradictions. 5 different versions of string theory, each promising to be the one true narrative. In a real trial, 5 mutually exclusive alibis are rarely a sign of innocence. And that wasn't all. The prosecution was about to call in a heavy hitter. Richard Feynman took the stand, and with surgical precision, tore through the defense's increasingly tangled testimony. String theorists don't make predictions, they make excuses. I do feel strongly that this is nonsense. I can't help it. Perhaps I could entertain future historians by saying I think all of this superstring stuff is crazy and is in the wrong direction. I don't like that for anything that disagrees with experiment, they cook up an explanation, a fix-up to say, well, it still might be true. It has to be excused most of the time. Doesn't look right. Here, the prosecution landed its sharpest counterpunch yet. Beauty, they argued, hadn't become a compass, but a mask, a way of evading reality whenever reality failed to comply. Every time string theory was challenged, instead of collapsing, it shapeshifted. And so if string theorists were going to make headway and convince the restless jury, they clearly were going to have to choose which string theory was the right one. Or maybe they wouldn't have to. It was very clear that if I didn't spend my life concentrating on string theory, I would simply be missing my life's calling. Is this on? It was with these innocuous words that Ed Witten stepped to the front of the lecture theatre at the University of Southern California in 1995. Wearing a black suit, a red tie, and thick-rimmed spectacles, his voice was high and squeaky, and he was about to change physics forever. Indeed, physics has often been reshaped by nomads who crossed scientific borders. Einstein, the patent clerk who remade space and time, Claude Lovelace, the mathematician who solved string theory's problems through extra dimensions when no one else could. But nobody has embodied this pattern more completely than Ed Witten. Witten initially studied history, then tried economics, then philosophy. Only then did he finally turn to physics, and yet within a decade of doing so, he was being hailed as the greatest living theoretical physicist, a man whose command of mathematics was so complete that colleagues compared him not to other scientists, but to Mozart. It's hard to put into words the esteem with which Witten is now held by large parts of the physics community. By 1990, people were already calling him the smartest living physicist, and that year he became the first physicist ever to receive the prestigious mathematics prize, the Fields Medal. So when Witten stepped up to speak at the Future Perspectives in String Theory conference in March 1995, expectations were already sky high. Heads turned, notebooks opened. Everyone wanted to hear what Witten had to say. Within physics, the big revelations don't arrive in wood-panelled courtrooms or in front of gavel-wielding judges. They happen at blackboards, in lecture theatres and on the conference floor. And so on that day, at the University of Southern California, the stage became the de facto courtroom of theoretical physics, and the jury was packed. But Witten hadn't come to this makeshift court empty-handed. The key to his new defense? Something called dualities. Physics is full of dualities. Perhaps the most famous is wave-particle duality. Sometimes light behaves like a wave, but other times it behaves like a particle. It all depends on exactly how you look at it. In the years after the first superstring revolution, physicists began to look for dualities between the 5 possible superstring theories, in an effort to make sense of them. And in doing so, interesting relationships began to emerge. In 1987, Balachandran Sathiapalan published an obscure, initially overlooked paper in which he explored the idea of T-duality. In this case, T stands for target space, the regions that strings are able to move in. To understand this, imagine that one of the extra, hidden dimensions invoked by superstring theories is curled up in a circle or a loop. A string like this can do one of 2 things. It can either travel in a circle along the loop, or it can wrap and twist itself around the loop. Sathiapalan's big insight was to realize something remarkable. A string traveling along a small circle is exactly the same as a string wound around a large circle. Similarly, a string traveling along a large circle is the same as a string wound around a small circle. And this meant that 2 of Green and Schwartz's superstring theories were identical. The apparent differences simply stemming from the fact that we're looking at them through different sized lenses. Like light behaving as a wave when traveling and a particle when interacting, at their heart, they are one and the same. One heads, the other tails, but it's still the same coin. And as well as this, the 2 heterotic string theories were also found to be identical in this way. T-duality means that really there are only 3 superstring theories, not 5. We shouldn't double count those that are mathematically identical. And T-duality was just the beginning. Crystal clear waves lap against miles and miles of soft, white sand. Nestled in the Caribbean Sea, 12 miles off the coast of Venezuela, Margarita Island is a little slice of paradise. And in the summer of 1974, a 14-year-old Anna Maria Font moved to the island with her family. It was on Margarita Island that Anna Maria would complete her final year of high school. And despite the remote location, Font fondly recalls how the chemistry and physics lectures included regular lab sessions. She soon became enthralled. After leaving Margarita Island behind, Font moved to the Venezuelan capital Caracas to study physics. Next on her meandering itinerary was Austin, Texas, where she would complete her PhD in 1987 amid the heady days of the first superstring revolution. And 3 years later came a sizable breakthrough. In 1990, a new type of duality entered the lexicon of string theorists. Thanks to the work of Font and her colleagues Luis Ibáñez, Dieter Lust and Fernando Quevedo, something called S-duality was applied to string theory for the first time, or to give it its full name, strong-weak duality. To understand S-duality, let's return to the shores of Margarita Island. Water is a miraculous material. It can be liquid, as in the Caribbean Sea, but it can also become ice and steam. These 3 states of water look and behave incredibly differently, but they all contain the same underlying water molecules. The only difference is temperature. When it comes to S-duality, temperature is replaced with interaction strength. how likely strings are to break apart or join up with other strings. In liquid water, the H2O molecules are relatively free to move and interact weakly, whereas in ice, they are rigidly bound and interact strongly. These two differing amounts of particle interactions are responsible for the contrasting behavior of water and ice, but it is still just one substance in two different states. And so through their work on S-duality, Font and her colleagues were able to show that one of Green and Schwartz's string theories was due to one of the heterotic string theories of the Princeton String Quartet. Not two separate theories at all, but a single theory glimpsed through two different lenses, as if ice and water had been misfiled as separate substances. The discovery of both T and S dualities clearly showed that the 5 superstring theories were not to be considered in isolation. There were deep, intimate and profound connections between them, and this was more than enough to turn Ed Witten's head, and he ferociously set about exploring further links between the 5 superstring theories. When Witten stepped up to the overhead projector at the String Theory Conference in March 1995, he was ready to reveal to the audience a series of staggering truths. The universe does not have 10 dimensions after all, he said. It has 11. There were not 5 different superstring theories, there was just one. The audience looked on wide-eyed and wide-mouthed. However, it would be wrong to give Witten all of the credit. Indeed, his talk was not the first hint of a possible 11th dimension. Back in 1978, Eugene Kremer, Bernard Julia and Joel Shirk had shown that 11 was the maximum number of dimensions possible if you wanted to preserve both supersymmetry and a single type of graviton. This 11-dimensional theory was known as supergravity. The trouble was, physicists had no evidence it was true. Just weeks before Witten's talk, British physicists Christopher Hull and Paul Townsend proposed something else extraordinary: that the 5 known string theories and 11-dimensional supergravity were not separate at all, but different parts of one deeper theory. Their paper, Unity of Superstring Dualities, lit the match. Witten set it ablaze. One thing that is certain is that Witten was the one to name this brave new world. He called it M-theory. And physicists once again had a single theory of everything. Witten's talk is now regarded as a landmark moment in string theory and quickly ushered in the second string theory revolution, just over a decade after the first. The defense team had wrenched back the upper hand. To understand the basic idea of M-theory, take a look at 3 shadows on the inside of a box. The shadows are all different shapes, so it would be natural to assume that they are being cast by 3 separate objects. However, they aren't. With one 3D object, 3 different 2D shadows can appear, depending on the direction of the torch beam. And in the same way, in Witten's mysterious new world, there is only one 11-dimensional theory. The 5 10-dimensional superstring theories that physicists had been struggling to choose between were the equivalent of the shadows. Everything was actually one. There has been much confusion over what the M in M-theory is meant to stand for. Witten himself has said that it could stand for magic or mystery, but much later did concede, "I thought my colleagues would understand that it really stood for membrane." Membranes, or branes for short, play an indispensable role in M-theory. If a string is a 1-dimensional object, one specific type of brane is a 2-dimensional sheet. And Witten realized that if you wrap one of these 2D branes around the 11th dimension, then it would look like a 1D string. Just as compactifying 6 dimensions of a 10-dimensional superstring theory looks like our everyday 4D world, compactifying the 11th dimension of M-theory looks like the 5 10-dimensional superstring theories. And so, M-theory relegates strings from their privileged position as the most fundamental building blocks of the universe. Everything is atoms, Atoms are subatomic particles are strings, and strings are just one kind of brain. And yet there is more than one type of brain in M-theory, and understanding what they are and the differences between them is a vital step in grasping what followed now that Witten had opened the floodgates and kick-started the second superstring revolution. Imagine reality is a grand and beautiful library. The open strings that make up ordinary particles are its books. However, brains are what the library itself is built from. Just as in a real library, books cannot simply float in mid-air. They must rest on shelves. These shelves are called Dirichlet brains, or D-brains for short. Without D-brains, open strings would have nowhere to end, and many of the familiar subatomic particles and forces we know would vanish. As well as this, there are the more structural M-brains, the equivalent of the library walls. M-theory contains two fundamental types, the two-dimensional M2 brain and the 5-dimensional M5 brain. Wrap an M5 brain around the 11th dimension in just the right way, and from the perspective of a 10-dimensional theory, it can appear as a D-brain. At first, this may not seem so strange, but it's actually like folding part of a vast wall in the library so that it becomes a row of shelves. From one perspective, it's still a wall, but from another, it now supports books, D-brains emerging from the geometry of M-brains. Simple. And mere months after Witten's talk, a further crucial breakthrough would emerge as the second superstring revolution reached fever pitch. Joseph Polchinski was ready to testify with the most surprising evidence yet. I could feel my heart pounding. It was one of those moments when you realize that something deep and true has been found, that the world is not as you thought it was. Writing in his memoirs, Polchinski recalls how it felt to make the breakthrough of his life. A life, tragically, cut short. Those memoirs were written while he was battling brain cancer, a battle that he would ultimately lose in 2018, at the age of just 63. If there's one thing I hope I'm remembered for, it's the realization that D-brains are physical objects. Before Polchinski, D-brains were treated like the Earth's equator, or rotation axis. Useful, but imaginary. Lines on a map don't bend the planet. But Polchinski showed that D-brains are real. We wouldn't be able to see them directly. They live in the extra dimensions string theory demands, yet they would be physical objects. They have mass, they carry charge, and their presence could warp the very fabric of the universe. What began as notional shelves for open strings turned out to be massive structures that can bend the space within the library itself. And so what had been dismissed as mathematical window dressing was now material fact. It was as if the defense had finally produced a key piece of forensic evidence: fingerprints at the scene. Polchinski almost didn't publish this key insight, thinking it might be too speculative, a hesitation that could have delayed the entire second superstring revolution. Indeed, it's the mark of a humble and cautious man. Polchinski's obituary in the New York Times focused just as much on his kindness and thoughtfulness as on his brilliance. With the second superstring revolution now firmly underway, physicists had once more shocked the theory back to life. What had looked like an intractable problem, 5 superstring theories, not one, had been seemingly resolved. Once more, there was a single theory to work with, one that not only promised to unite quantum physics with gravity, but also offered a framework for understanding subatomic particles and their interactions. All that was needed was yet another hidden dimension. For the defense, this was a rare moment of solid ground. The phantom scaffolding of the theory seemed suddenly tangible. The shelves were real. They carried charge, they bent space. Beauty, at least for a moment, looked as if it might be anchored to reality. However, the prosecution was unmoved. not a single experiment had glimpsed these hidden structures, and so for now, the jury could only mark it as another point scored for beauty and elegance, not for evidence. The defense had produced structure, but the prosecution wanted sightings. Yet Polchinski's discovery did have a sting in its tail. What if, in some strange and beautiful way, the bookshelves knew everything about the rooms they stood in? What if the laws etched on these shelves somehow encoded the architecture of the library itself? Soon, this would become more than metaphor. It would become a blueprint for an entirely different kind of universe, one where space, time, and gravity itself might be a projection. It is more important to have beauty in one's equations than to have them fit experiment. In 1997, a young Argentine physicist named Juan Maldacena published a paper that shook the courtroom to its foundations and would go on to become the most cited in string theory's history. Yet Maldacena himself never anticipated the scale of the impact. At the time, I thought maybe a few people would be interested. Indeed, to this day, he remains almost bashful about it. He never raised his voice and rarely used more words than strictly necessary, said one colleague. And so as others projected cosmic significance onto his equations, Maldacena quietly returned to work, content to let the mathematics speak for itself. Maldacena's big idea went by the rather arcane name of the ADS-CFT correspondence, and this obtuse title belied a dizzying new possibility, born out of the exploration of strings and brains, that the entire universe could be a hologram. To begin to understand the intricate physics behind Maldacena's ADS-CFT correspondence, let's return to the grand library of the universe. Polchinski had shown that D-branes weren't just a mathematical framework. They could be physical objects, the library's bookshelves. Open strings, like books, could end on them. But more than that, these shelves had mass and charge, and could warp the architecture of the library itself. D-branes came in various sizes. A D0 brane is a point-like shelf, a D1 brane is a one-dimensional string-like one, and a D3 brane spans 3 spatial dimensions, the same dimensionality as the space we inhabit. Maldacena asked, what happens when you stack many of these D3 branes together, in effect, filling a section of the library with this familiar shelving? And what he uncovered was extraordinary. The sheer mass and energy of the stacked D3 branes warps the library to such an extent that space curves inwards. This inward bend is the hallmark of anti-de Sitter space, the ADS in Maldacena's theory. And there was more. The open strings moving on the D3 branes gave rise to a quantum field theory with a remarkable symmetry, a conformal field theory, the CFT part. And while this type of theory is not quite our quantum physics, it shares much of the same mathematical structure. Not siblings exactly, but close cousins built from similar foundations. And it was here that lay the radical heart of Maldacena's proposal. This quantum field theory doesn't live inside the warped library. It lives on its boundary. Imagine a 2D screen on the library's outer wall showing everything happening inside. You never need to step into the hall. Every event is faithfully recorded on that screen. But this screen is no mere facsimile. It doesn't just reflect the interior. It is the interior, written in a different language. Every physical process occurring within the library, every book being borrowed, every rearrangement of its shelves, has a precise counterpart on the screen. Those events exist there too, fully and exactly, just expressed through a different, quantum set of rules. This is Maldaceno's ADS-CFT correspondence. This wasn't a cross-examination or a rebuttal, it was something else entirely. Maldaceno's holographic universe didn't just answer questions, it redefined what the questions should be. Beauty had returned in a most unfamiliar guise, forcing the jury to reconsider the very nature of the case. A universe with gravity, contorting under the influence of mass and energy, somehow encoded in a lower dimensional quantum theory that doesn't even know how to include gravity. The curvature of space, the relentless pulling of stars on planets, even the very fabric of space-time itself, all of it could be translated, line by line, into the cold language of quantum fields on the boundary. And so yes, in this sense, ADS-CFT is a kind of hologram. Think of the holograms often found on the back of a bank card. All the information is encoded in just 2 dimensions, yet it gives rise to an equivalent 3D image when viewed from the right perspective. Similarly, in this theory, a 5-dimensional world with gravity could emerge entirely from a 4-dimensional boundary with no gravity at all. Concepts this radical come along once in a generation at best. If true, Maldaceno's idea would be as paradigm-shifting as discovering the Earth orbits the Sun or that time dilates with speed. It forces physicists to question assumptions they once considered immutable, that gravity is real and space has substance. But, unfortunately, it turned out we didn't live in this kind of universe. Anti-de Sitter space has negative curvature, where the angles in a triangle add up to less than 180 degrees, and the best astronomical observations available at the time suggested that space is, in fact, flat, with no curvature at all. But despite this, however, ADS-CFT may be pointing towards something deeper. It suggests that gravity and space-time might not be fundamental, but emergent, woven from more basic quantum interactions on a lower dimensional boundary. And so even though our universe didn't appear to be built from anti-de Sitter space, Maldaceno's duality hinted at a broader principle, that the fabric of space itself could be a kind of hologram. And nowhere is this holographic principle more sharply tested than with black holes. The most extreme objects in the universe, where general relativity and quantum mechanics directly contradict each other. And resolving that contradiction is precisely what string theory was built to do. In particular, black holes raise a question that neither theory can answer alone. What happens to information that falls in? This is the infamous black hole information paradox. And to explain this, the court now calls Jacob Bekenstein to the stand. Born in Mexico City in 1947, Bekenstein saw the spiritual side of science. I look at the world as a product of God. He set very specific laws, and we delight in discovering them through scientific work, he once told the Israeli newspaper Haaretz. But if there's any place in the universe that stands as the antithesis of heaven, it's probably a black hole. Inescapable chasms in the very fabric of space-time, they relentlessly heave and hoard. Matter is drawn inexorably inwards towards an event horizon, torn limb from limb before vanishing over the edge of the gravitational waterfall, gone forever. Or maybe not. For in 1972, Bekenstein founded the field of black hole thermodynamics, an achievement that would eerily foreshadow Maldaceno's work a quarter of a century later. For at its heart, thermodynamics is the study of a property known as entropy, a measure of how many ways a system can be rearranged internally without changing its outward appearance. More possibilities means higher entropy. And so to understand this, imagine hurling a book over the event horizon of a black hole. According to general relativity, black holes can be completely described by just 3 properties: their mass, their charge, and their spin. Of course, your book adds a tiny bit of mass, but all the fine-grained details about what was on each page, the carefully crafted characters and narrative arcs, appear to vanish. And therein lies a problem, for the second law of thermodynamics explicitly forbids the destruction of entropy. It must always increase or remain constant. Bekenstein's breakthrough was to propose that the black hole responds to your book by increasing the area of its event horizon, and that this area functions as a kind of entropy. And in doing so, he preserved the second law and hinted at a deeper truth: that the black hole's boundary somehow stores information about everything inside. That sounds a lot like ADS-CFT correspondence. But a deeper problem remained. In 1974, Stephen Hawking showed that black holes aren't entirely black. They emit radiation. Indeed, over immense timescales, it was revealed that a black hole can evaporate completely. This therefore created a new paradox. Hawking radiation was featureless, carrying no imprint of what fell in. When the black hole was gone for good, so was all the information it once contained. This violated not just thermodynamics, but the core of quantum mechanics, which insists that information cannot be destroyed. And this was the paradox, a conflict not between specific theories, but between the foundational rules of physics themselves. And it would take the machinery of string theory and the radical duality of ADS-CFT to begin to resolve it. And here, perhaps, the courtroom reaches its tensest moment. What began as a case about strings and particles has become a trial over the very nature of space, time, and information itself. Let's return once more to our grand ADS-CFT library. From inside the library, when a black hole forms and eventually evaporates, it seems as though information about what it swallowed has been lost. A book thrown into the gravitational abyss appears to vanish without a trace, but the screen on the boundary wall, the boundary quantum theory, keeps a perfect record. In the language of the screen, nothing is ever truly lost. The ADS-CFT correspondence tells us that these two descriptions, the interior view with gravity and the screen's quantum field theory without gravity, are mathematically equivalent. So if the screen evolves in a way that preserves information, then the entire library must as well. What looked like destruction from a gravitational perspective is, from the boundary's point of view, just a particularly complicated translation. And so the black hole information paradox becomes not a failure of physics, but a sign that space, gravity, and information are woven together more tightly than we'd ever imagined. But of course, though ADS-CFT may seem to provide a compelling resolution to the black hole information paradox, it does so in a universe we don't inhabit. After all, we don't live in anti-de Sitter space. And so again, the theory's insights are deep and possibly universal, but we still don't know how to apply it to the real universe. And so with Maldasena's duality, the courtroom reeled. Beauty had taken the stand in its purest form. An entire universe projected onto a two-dimensional screen. For the defense, it was a masterstroke. For the prosecution, just more speculation in silk robes, the emperor's new clothes. Once more, the jury was suspended between wonder and doubt, dazzled by beauty, but starved of proof. Indeed, there are those that loathe this approach to physics, not least the fact that the theory is currently impossible to test or falsify. Some argued that physicists were so desperate to reconcile quantum theory with gravity that they'd lost sight of the most fundamental aspect of a good scientific theory, that it should make testable predictions. Physicist Lee Smolin once remarked, "It's not really a theory, it's a conjecture about a theory that we would love to believe in." The prosecution pounced. To them, Maldasena's entire testimony reeked of speculation. No crime scene, No fingerprints, no verifiable timeline, just elegant conjectures stacked atop untestable assumptions. Impressively told circumstantial evidence, at best. Theoretical physics, they reminded the jury, should not be judged by aesthetic appeal, but by experimental accountability. Until ADS-CFT made contact with measurable reality, until it predicted something nature could confirm or deny, it remained, in the prosecution's eyes, an exquisite, outlandish guess. Not for the first time, the defense team was scrambling. Then, just as they began to regroup, the universe threw them another potentially catastrophic curveball. You may find that your most elegant theory, the one you like the best, is simply wrong. It is the opening days of 1998. Bill Clinton is president. Elton John's reworked Candle in the Wind, a tribute to Princess Diana, is finishing its 14-week run at the top of the US charts. Titanic is still packing cinemas. And against this cultural backdrop, the American Astronomical Society is holding its annual meeting in Washington, D.C. Journalists and scientists pack the room to hear from astronomer Sol Perlmutter. On the screen, a decade's worth of data reduced to dots and lines. What he is about to reveal would later win him a share of the 2011 Nobel Prize in Physics. Yet in the courtroom of theoretical physics, this was a hostile witness, one summoned from a completely different field with no loyalty to string theory, and the evidence Perlmutter presented would leave the defense scrambling and hand the prosecution an explosive new line of attack. The vast majority of astronomers and cosmologists accept that the universe began in an event known as the Big Bang, nearly 14 billion years ago. It started out unimaginably small, far tinier than an atom, and has been expanding ever since, ballooning into the cosmos we see today. But by now, many eons later, that expansion should be slowing down. The gravitational pull of all the stuff in the universe, stars, gas, galaxies, dark matter, ought to be applying the brakes. And in the mid-1990s, as the second superstring revolution roiled through theoretical physics, two teams of astronomers had been busy trying to confirm that deceleration. It was supposed to just be a routine check. But when Perlmutter announced his team's results at that press conference in early 1998, they stunned the astronomical community. For string theorists, it was a bombshell in open court, a line of evidence they hadn't anticipated, and one they had no ready answer for. Both teams had been using exploding stars, called Type 1a supernovae, to track the expansion history of the universe. These cosmic detonations occur in binary systems, where a dead, dense white dwarf orbits alongside an ordinary star. Over time, the white dwarf's gravity siphons material from its companion, slowly growing heavier. But its appetite has a hard limit. Once the white dwarf nears a critical mass, about 1.4 times that of the Sun, known as the Chandrasekhar limit, it becomes unstable. A wave of thermonuclear reactions rips through it, and the star is blown apart. But what makes Type 1a supernovae so useful is that they all explode with roughly the same amount of fuel. That means they all shine with roughly the same intrinsic brightness. Astronomers call them standard candles, and by comparing how bright they appear to how bright they should be, they can determine their distance. The dimmest are the furthest away. Except the two rival teams, Perlmutter's Supernova Cosmology Project and the HiZ Supernova Search Team, both found something deeply unexpected. The distant supernovae were too dim. Not just farther than expected, but as if space had expanded more than it should have since their light began its journey towards us. And the only explanation was shocking. The expansion of the universe wasn't slowing down, it was speeding up. Even today, astronomers have no definitive answer as to why this is happening. The The accelerating expansion is usually put down to something called dark energy, a shadowy entity whose potency only grows as the universe ages. What dark energy actually is, however, remains, well, dark. But what we do know is that dark energy implies something about a term in Einstein's equations, the cosmological constant, usually denoted by the Greek letter lambda. Einstein originally introduced it as a mathematical fix to hold the universe still, and when Edwin Hubble discovered the universe was actually expanding, Einstein realized his error. But lambda wasn't a mistake after all. Today it's clear that the cosmological constant, the amount of energy that occupies all of empty space, or something acting like that, is real, and it's driving the acceleration. And more than just setting space's expansion rate, lambda also affects its geometry. If this energy is negative, the universe has negative curvature. And if it's positive, as the supernovae data seem to suggest, the universe has positive curvature. And this was, and is, a big problem for string theory. We've seen negative curvature before. When Polchinski stacked D3 brains in our holographic library, the mass and charge of the brains warped the space, curving the library walls inwards. Indeed, that's anti-de Sitter, ADS geometry with negative curvature. But now, a fundamental cosmological measurement was telling us that the real universe curves the other way. The walls don't cave in, they bulge outwards. In geometric terms, we didn't live in an anti-de Sitter space with negative curvature, but in a de Sitter-like universe, where the curvature is positive and the expansion accelerates indefinitely. And that's not merely a mismatch, it strikes at the heart of the most mathematically mature part of M-theory. ADS-CFT, for all its evidence, turned out to be built on a geometry that clearly clashes with astronomical observations. Speaking in 2001, Ed Witten said, "I don't know of any clear way to get de Sitter space from string theory or M-theory." This was a damning admission from string theory's biggest star witness. The defense was once again on the ropes. With no explanation for dark energy, the prosecution smelt blood. And though what followed wasn't a knockout blow, it might be the defense's last chance to stay on its feet. Desperate, the defense team called Renata Kalosh to the stand. Kalosh was born in 1943 in the culturally rich city of Chernivtsi, now part of Ukraine, amid the upheaval of World War II. She came of age during the Khrushchev thaw, a period of relative openness and reform following Stalin's death. Against this backdrop, Kalosh moved to Moscow to study physics, and by 1968 she'd earned her PhD from the capital's prestigious Lebedev Physical Institute. She would also find love there. Seminars on cosmological phase transitions aren't typically known as hotbeds of romance, but it was during one such seminar that she caught the eye of fellow physicist Andrei Linde. They began talking about physics, and 2 years later they met again, this time at Lake Ladoga near St. Petersburg. "When I was leaving Ladoga, I kept Renata's hand in mine just a second longer than I was supposed to," Linde recalls. "A few months later, we were married." The couple recently celebrated their golden wedding anniversary. Kalosh and Linde quickly became a physics power couple. As the Soviet Union began to collapse, they left together, first for CERN and then in 1990 to accept joint professorships at Stanford University, home to one of the world's leading centers for cosmology and theoretical physics. And they were still at Stanford in 2003 when they helped develop an idea that might rescue string theory from the existential quagmire brought on by the discovery of dark energy. Working alongside Shamit Kachru and Sandeep Trivedi, they devised what became known as the KKLT mechanism, a moniker formed from the initials of their surnames. Back in the 1980s, amid the first superstring revolution, physicists had made headway in curling up the extra dimensions of string theory. The work of Calabi and Yau offered a way to fold the origami of the universe into intricate, compact shapes known as Calabi-Yau manifolds. But even by the early 21st century, this approach faced a serious problem. The folds weren't stable. The size and shape of these extra dimensions could fluctuate wildly, leading to universes that were either unstable or unrecognizable. And so, like the Green-Schwarz mechanism before it, the KKLT mechanism was a patch, a fix for a deeper flaw. First, it introduced fluxes, fields that thread through the folds of the extra dimensions, acting like invisible tape to hold the shape in place and prevent it from warping. But that alone wasn't enough. These solutions still tended to produce universes with negative curvature, anti-de Sitter space. And so to fix this, KKLT introduced anti-branes, objects with the opposite energy and charge to regular D-branes. Adding them tips the balance, finally producing a universe with positive curvature, just like the de Sitter space implied by the supernova results. But it turned out that there are a lot of ways to add fluxes and anti-branes to Calabi-Yau manifolds. Each one produces a different version of string theory, resulting in a different version of the universe, with its own laws of physics, particles, and forces. And this vast expanse of possibilities is known as the string theory landscape. But this landscape doesn't contain just a handful of different string theories, or even 1,000, not even 1,000,000, billion, or trillion different ways, but at least 100 quinquecentacentillion. That's a 1, followed by 500 zeros. It's hard to do justice to just how big a number that is. Compared to this 10 to 500 possible universes, the number of galaxies, stars, or even seconds since the Big Bang are mere rounding errors. Jacob Bekenstein once calculated the limit of how much information can be stored in a given region of space, and so if the entire observable universe were a cosmic hard drive, it could hold around 10 to the power of 122 bits of information. So adding the KKLT mechanism suddenly gave us more possible versions of string theory than there is information available in the entire universe to list them. No matter how smart we are, no matter the size of the computers we build, we can't ever hope to catalogue, simulate, or analyze them all. Even in principle, the computational and physical limits of the universe make that utterly impossible. And so if string theory had been accused of untestability before, it was now, in the eyes of its critics, irreparably so. To the prosecution, the defense had exchanged uniqueness for a wilderness of alibis. One such critic, Lee Smolin, didn't mince his words. If an attempt to construct a unique theory of nature leads to 10 to the power of 500 theories, that approach has been reduced to absurdity. The defense argued that this is simply what frontier physics looks like: messy, abstract, and occasionally lost in its own beauty. The prosecution, however, saw something very different, a theory not grounded in evidence, but permanently insulated from it. And so if string theory's defense team were to stop the judge and jury throwing out the case for good, they had some key blanks to fill in. If the universe is accelerating, not just coasting but racing away from itself, then we're dealing with something far stranger than anyone had planned for. Instead of a small tweak to the cosmic script, it was a complete rewrite of the opening scene. The trial was no longer just about strings or particles. With so many possibilities now on the table, the courtroom had become something else entirely. A grand inquest into not just how the universe exists, but why this particular version of it emerged from the vastness of possibility. And whatever the answer was, it wouldn't be local, it wouldn't be small, and it certainly wouldn't leave the early universe untouched. The great tragedy of science, the slaying of a beautiful hypothesis by an ugly fact. The sun rises slowly over a picture of serenity, a glassy pond with not a ripple to be seen. A cool, early morning mist clings to the calm waters as dragonflies dance between the reeds, the silence only broken by the occasional chirp of a cricket or croak of a frog. Though it may not seem like it, this picturesque pond shares a lot in common with the modern universe. It's seemingly calm, balanced, and most importantly, self-contained. Indeed, according to the theory of the Big Bang, this cosmic pond grew from a tiny puddle about 14 billion years ago. But like any seemingly still pond, you'd expect to find disturbances beneath the surface. Eddies, whirlpools, and currents. Yet instead of this, the more physicists studied the universe, the more unsettlingly still it became. The deeper they looked, the more uncanny the calm. And so in a sense, it wasn't what they saw that was alarming, it was what they didn't see. To begin with, there was the flatness problem. Just like the surface of the serene pond, space today appears to be very close to what astronomers call flat. In other words, it has almost no curvature at all. Any tiny deviation from flatness early on should have become exaggerated as space expanded, warping the surface into something visibly bent today. And yet instead, it's astonishingly smooth. At first glance, there are two possible explanations for this. Perhaps space was perfectly flat to begin with, and so simply stayed that way as it grew, a serene puddle growing into a serene pond. But the odds of that happening by chance are astronomically low. The second option is that the pond ballooned so enormously that any initial ripples were ironed out, flattened by sheer size. But the standard Big Bang model doesn't allow for nearly enough expansion to do the job. And then there's the horizon problem. Even though the pond is now vast, too wide for a ripple to have crossed from one bank to the other since it formed, the entire surface looks perfectly coordinated. No currents, no temperature differences, every part of the pond seems to have agreed on the same conditions. And that shouldn't be possible. For one side of a system to know about the other, to equalize, synchronize, or share information, something has to travel between them. A ripple, a current, a message in a bottle, something. But in our expanding pond, there simply hasn't been time for that. The banks are too far apart. There hasn't been enough time for ripples or information to reach from one side to the other, for everything to even out. The speed of light simply isn't fast enough to cover the distance in the time the universe has existed, and yet its opposite sides still appear identical. And finally, there's the monopole problem. Predicted particles that, like mythical leviathans lurking in the deep, should be swimming through the cosmos in droves. Magnetic poles without a partner, a south without a north without a south. Theories that try to unify the three non-gravitational forces suggest that at high energies, the early universe should have produced huge numbers of them, and yet we've never seen one. That's a serious problem for any theory aiming to describe physics at the highest energies, string theory included. And so each of these three problems alone was troubling. The three of them together was damning. The Big Bang was our best model of the early universe, but it was leaking at the seams. If no solution could be found, it might have to be abandoned altogether. And if even the Big Bang couldn't be trusted, how could grander frameworks like superstring theory, which sought to unify all of physics, hope to succeed? Luckily for superstring and the Big Bang theory, one man had a single idea that could patch every leak at once. The court calls Alan Guth to the stand. Born in 1947 in New Brunswick, New Jersey, Guth skipped his senior year of high school and enrolled at MIT at just 17, earning a bachelor's, master's, and a PhD all in quick succession. He began his career in particle physics, studying quarks, before shifting his focus to cosmology in the mid-1970s, drawn by puzzles like magnetic monopoles and the flatness of space. Yet Guth struggled and went from temporary post to temporary post. until late one night in December 1979, he experienced what he described at the time as a spectacular realization. Guth figured out that a period of rapid, exponential expansion could solve not one, but all three Big Bang problems. And by 1981, he had formally proposed what we now know as cosmic inflation, and his career, understandably, took off. Inflation is like an underground pipe beneath the pond. It provides a sort of pressure surge that for the briefest moment blasts huge quantities of water in from below. The puddle doesn't just grow, it erupts. Then the pipe shuts off, leaving the pond to expand at a slower, steadier pace. According to the theory, this initial inflationary phase saw the universe's size skyrocket from considerably smaller than an atom to about the size of a grapefruit in just a trillionth of a trillionth of a trillionth of a second, doubling in size roughly 80 times. That may not sound like much, but by the end of inflation, the universe was roughly 10 to the power of 78 times bigger than it had been at the start. To put that number into context, imagine taking an ordinary shipping container and then expanding it by the same amount. Suddenly, it would be larger than the entire observable universe. But how did this relatively straightforward addition solve all the problems of the Big Bang? Well, the flatness problem hinged on the fact that there hadn't been enough expansion since the Big Bang to smooth out any initial wrinkles. But inflation adds in the extra required expansion. Similarly, the horizon problem argued that there hasn't been enough time for ripples to travel between every part of the pond. Add in the extra expansion from inflation, and suddenly the puddle can start much smaller, much more interconnected, and still be capable of becoming the enormous pond we see today. And finally, what about the missing monopoles? Well, inflation solves that too. If monopoles were formed in the early universe, they would have been diluted by inflation's vast expansion of space, stretched so thinly across the cosmic pond that we'd expect to find hardly any at all. At first, inflation looked like a miracle cure. It fixed the flatness and horizon problems, and even swept the monopoles under the cosmic rug. But Guth's original idea, although highly elegant in theory, didn't quite work in practice. His version of inflation ended too violently, leaving behind a universe riddled with bubbles. And so, as it happened many times before in physics, Guth's original model was beautiful, but when pressed it cracked under cross-examination. The defense would need a smoother, more controlled version of the same idea. And that refinement would one day dramatically intersect with the world of string theory, and it came from a familiar face, Andre Linde. Guth's inflationary surge was too abrupt, like the underground pipe had burst. Linde added the equivalent of a pressure valve. The water still rushed in, expanding the pond dramatically, but now in a smoother, more controlled fashion. The surface could stay calm, coherent. And that wasn't the end of it. For in Linde's version, the valve didn't simply shut off all at once. One region of the pond might stop swelling and begin settling, but others could keep expanding. Some of those regions would even spawn new valves of their own, launching entirely new ponds. And this process would never end. Inflation became eternal. Our serene pond, just one amongst countless others, each with its own currents and contours, shaped by the exact circumstances of its birth. In other words, a vast and expansive landscape of ponds, with each one having its own particles, fundamental forces, and laws of physics. A multiverse. If this idea sounds familiar, it should. It's an eerie parallel of the string theory landscape. And so here was a completely separate theory, one born from an entirely different perspective, arriving at the same unsettling conclusion. A vast multitude of universes, each with its own unique physics fingerprint. Fixing the Big Bang theory suddenly brought it into close alignment with superstring theory. The defense's case began to glisten. But, just as the two theories seemed to be converging into something grander, deeper questions began to bubble up. Could these lush ponds, so elegantly imagined, be nothing more than mirages? To answer this question, the court summons Kamran Vafa. Vafa was born in 1960 in Tehran, the capital of Iran, during a period of profound political turbulence. The Shah was in the midst of a sweeping modernization campaign known as the White Revolution. When Vafa was 4, Ayatollah Khomeini, a fierce critic of the Shah's reforms, was exiled. That same year, the Iranian Prime Minister was assassinated in the street. And so with all of this happening around him, the young Vafa turned his eyes a little higher, to the moon. Whenever I would look at the moon, it was bothering me as to why it wouldn't fall to the ground. He would later recall, that fact stuck with me, and also why other people were not bothered by it and treated it as if it were irrelevant. These musings would kickstart a lifelong love affair with the biggest questions about our universe. This ensuing quest for answers took Vafa first to MIT, then to Princeton, where he completed his PhD in 1985 under the watchful eye of Ed Witten. And by 2008, he had made such important contributions to string theory that he was awarded the prestigious Dirac Medal alongside Juan Maldacena and Joseph Polchinski. And arguably Vafa's most provocative insight had come 3 years before, in 2005. A sharp, unsettling idea that threatened to throw both string theory and inflationary cosmology into disarray. Welcome to the Swampland. Vafa looked out across the seemingly boundless landscape of inflationary ponds, each one a possible universe with its own shape and physics, and asked a simple question. Were any of them actually compatible with string theory? And in case after case, the answer came back a resounding no. No matter how you tweaked the geometry or rearranged the ingredients, these pond-like universes refused to form. Or worse, they emerged only by violating principles string theory seems to uphold everywhere else, like how forces should behave or how light particles can be. In other words, not every mathematically consistent pond is actually physically viable. Some of them may look placid and still, but step in and you'll find yourself sinking deep into the mud. What had seemed like a serene pond turns out to be a slurried, stinking mess. Together, these boggy outcrops make up Vafa's Swampland, a murky, unstable region of the inflationary landscape that cannot be derived from string theory no matter how hard you try. Swampland had serious teeth. Vafa's conjectures aren't proven, but they function like legal precedent, setting the boundaries any defense must reckon with. And so what once seemed like safe theoretical ground was suddenly treacherous. Vafa wasn't just surveying the landscape, he was issuing injunctions. Entire regions were now off limits. Vafa and others now began deriving specific mathematical tripwires, constraints that any viable universe must avoid. Many existing theories stumbled right into them. One of the biggest casualties was Kolosh and Linde's KKLT mechanism. Most known KKLT-type solutions sit squarely in Vafa's Swampland. This is a massive problem for string theorists because they need the KKLT mechanism to stabilize the theory and make it compatible with the accelerating expansion of the universe. And indeed, Vafa's tripwires also entangle the theory of inflation itself. In particular, they hit slow-roll inflation hard, the gentle, controlled expansion described by Linde. According to the Swampland criteria, the conditions needed for such a smooth and steady growth may simply not be allowed. The process unfolds too slowly, or stretches too far, or relies on a kind of delicate balance that string theory seems unwilling to permit. For critics, this was damning. String theory couldn't comfortably accommodate the best-known explanations for either dark energy or inflation. If the Swampland conjectures are right, then two of the most widely accepted pillars of modern cosmology are mutually incompatible with string theory. Not flawed approximations, fundamentally incompatible. although inflation does at least have one advantage over KKLT: it might be testable. One of the most promising tests comes in the form of primordial gravitational waves. Inflation should have left its mark, either through subtle distortions in the light left over from the Big Bang, or as faint waves still travelling through the universe today. And several experiments are hunting for them. Ground-based observatories, like BICEP and the Simons Observatory, scan the sky for signatures in the leftover light. Soon, a space-based mission will join the chase. LISA, the Laser Interferometer Space Antenna. Scheduled for launch in the 2030s, LISA will be the first gravitational wave observatory in space, exquisitely sensitive to low-frequency waves that ground-based detectors can't catch. If LISA does see the right kind of background signal, it could offer direct evidence that inflation really did shake the universe into being. But of course, even this wouldn't resolve the deeper question. For proving inflation shaped our pond is one thing, but proving it filled a multiverse of ponds is quite another. Eternal inflation may be compelling, but it remains difficult, maybe impossible, to falsify. Indeed, critics have long warned that it risks slipping from science into metaphysics. Paul Steinhardt, one of the original architects of inflation, has since become one of its most vocal detractors. He now argues that inflation has become a self-justifying idea, impossible to rule out and ever more baroque in its defense. It's the same criticism we've seen thrown at string theory, time and time again. And so, we reach an impasse. Inflation may be right, but it's slippery. KKLT may be beautiful, but it's inadmissible. The case had grown enormous, a legal skyscraper of claims and counterclaims. But at its foundation sat one quiet, unproven assumption: supersymmetry. Indeed, the entire defense rested on it. After all, there could be no superstring theory without supersymmetry. And yet now, after decades, the court was finally ready to test it. Supersymmetry is the distinctive prediction of string theory that is most likely to be discovered experimentally. The sprawling ice sheets of Antarctica are a white, bleak wasteland. There is nothing for miles save for snowstorms and blizzards, yet as we converge on the geographic South Pole, human-made castles rise above the permafrost. For here, on the high plateau of Antarctica, some 2,835 meters above sea level, is the Amundsen Scott South Pole Station. And among the dozens of buildings that dominate the otherwise desolate landscape is IceCube, a state-of-the-art neutrino observatory. And yet the truly impressive part of IceCube is found underground. In 2005, the very same year Cameron Vaffer went public with Swampland, engineers began using drilling towers and warm water hoses to bore deep holes into the Antarctic ice. Into each, they lowered long strings with detectors hanging on the ends. The harsh conditions and inhospitable winters, where the sun doesn't rise for months on end, meant IceCube took 5 long years to complete. Thousands of sensors were spread over a cubic kilometer of ice, making it the largest neutrino telescope in the world. And indeed, IceCube's bread and butter is high-energy neutrinos, produced by calamitous events in the deep, far-off universe. And yet it also has its subterranean eyes set a little closer to home. For IceCube is on the lookout for neutrinos being hurled up from the core of the Earth. Neutrinos produced by dark matter. If dark energy had been an agonizing thorn in string theory's side, dark matter might yet prove a powerful ally. As we've seen already, dark energy is the mysterious entity that appears to be accelerating the universe's expansion. Dark matter, however, in a sense plays the opposite role. It is the invisible glue that binds cosmic structures together. Astronomers first noticed dark matter's effects as far back as the 1930s. Galaxies within clusters seemed to be moving too fast, and one way to explain why these clusters didn't simply fly apart is if there was hidden material inside, exerting an extra gravitational pull. Indeed, individual galaxies told a similar story. Stars on their edges orbited faster than expected. Perhaps, astronomers mused, they too were held in place by some invisible adhesive. At first, though, scientists were stumped as to what dark matter could be made of. The culprit seemed to have two properties. It must have mass, otherwise it wouldn't exert gravity, and it must not interact with light, otherwise we'd see it. Unfortunately, no suspect in the standard model lineup matched that particular fit, and so they wondered, could dark matter be lurking beyond the standard model? Astronomers' interest in dark matter accelerated in the 1970s, just as string theorists were beginning to juggle with supersymmetry. And it turned out that the lightest supersymmetric particle, the neutralino, would behave just like dark matter. It is a form of weakly interacting massive particle, or WIMP for short. And from that moment to this, the search for WIMPs gathered pace. And so it seemed that supersymmetry didn't just streamline string theory, it also seemed to predict one of the most fundamental aspects of our universe. Finding WIMPs, therefore, would be a ringing endorsement of supersymmetry and bolster the case for string theory to boot. And indeed, despite all its promise with dark matter, supersymmetry also had an older alibi. After all, it was supersymmetry that first let string theory smuggle gravity into quantum mechanics. Without it, string theory's cleanest prediction, the graviton, vanishes. And without the graviton, the whole defense begins to unravel at a precipitous pace. And so string theorists pinned their hopes on the detectors hidden beneath the ice. If the galaxy is indeed flooded with WIMPs, the solar system should be plunging through them as it orbits around the Milky Way. Dark matter particles should continually sink into the core of the Earth, where they would collide with one another and produce neutrinos. Neutrinos that Ice Cube has been looking for. Simple enough, except for the fact it hasn't seen any. Indeed, a study released in early 2025 trawled through a decade of Ice Cube data and found absolutely no signatures of dark matter coming from the center of the Earth. Perhaps scientists thought another team would have more luck, this time with an experiment not tucked away under the Antarctic ice, but hidden a mile underneath South Dakota in an abandoned gold mine. Except, once again, the search here, with the Lux Zeppelin experiment, also came up short. But perhaps the heady maelstrom of the galactic center, where stars and dust are constantly swirling around a gargantuan supermassive black hole, offers more possibility for WIMPs. Indeed, another experiment has been scouring this region for clues, the Alpha Magnetic Spectrometer. Bolted to the side of the International Space Station, AMSO-2 is a hulking $2 billion cosmic ray detector. Since 2011, it's been measuring high-energy particles that might be produced by WIMP annihilations near the galactic center. And initial results looked promising. AMSO-2 found more positrons than expected, raising hopes that dark matter might be the culprit. But, again, the signal proved ambiguous. Pulsars, rapidly spinning neutron stars, could produce the same excess. This means that more than a decade on, physicists are still debating what, if anything, AMSO-2 has seen. And so, the result is frustratingly familiar. Hints, suggestions, and shadows, but never certainty. The evidence for supersymmetry through dark matter searches remains agonizingly elusive. But there is another way. The most direct tests of supersymmetry have taken place at the largest energies achievable on Earth, at the Large Hadron Collider. Here, beneath the French-Swiss border, protons are smashed together at near-light speeds, in the hope that something entirely new might emerge. If supersymmetric particles exist, Some should be within the Large Hadron Collider's reach. The LHC first turned on to much fanfare towards the end of 2008, and within 4 years it made headlines around the world when physicists discovered the Higgs boson, the much-lauded God particle. The Higgs boson and the associated Higgs field is what gives other particles mass. And yet the discovery of the Higgs threw up a confounding mystery. It was a lot lighter than physicists had expected. With mass and energy interchangeable, the energy of the Higgs field was surprisingly low, and this meant that supersymmetry became a white knight, riding in to save the day. This is because if ordinary particles have sparticle partners, they would partly cancel each other out, leading to a low-energy Higgs field. Add in the ability to explain dark matter and the unification of forces at high energies, and supersymmetry seemed to hold the upper hand. And yet, that cancellation only works if sparticles are also relatively light. The heavier they are, the harder it is to use them to square away the lowly mass of the Higgs. And this was the problem. The LHC is smashing particles together with such ferocity that it should be producing sparticles at the lighter end of what is possible. And yet once again, like Ice Cube and Lux, the silence was deafening. The jury heard the hush as loudly as any testimony. As the prosecution pressed home the advantage, the defense scrambled for explanations. Maybe light sparticles do exist, but somehow the LHC is missing them. It's unlikely, but possible. More likely is that if sparticles do exist, they're too heavy for the LHC to produce at current energies. But that then makes it nearly impossible for supersymmetry to explain the featherweight mass of the Higgs. To the jury, it sounded less like confidence and more like backtracking. For decades, supersymmetry had been the defense's star witness, beauty incarnate, the promise that string theory could finally make contact with reality. Now that witness looked evasive, its testimony collapsing under cross-examination. And even that still wasn't the end. For the higher the mass of the sparticles becomes, the harder it is to use supersymmetry to explain the full triumvirate of dark matter, force unification, and Higgs mass. Physicists are forced to fine-tune the theory with surgical precision, undermining much of supersymmetry's original far-reaching appeal. And so yet again, when confronted with a deluge of experimental evidence to the contrary, the defense team seems to squirm and wriggle its way out of it. In an essay aimed at his peers, physicist Mikhail Schiffman has urged them to stop developing continued, Baroque-like, aesthetically unappealing modifications to supersymmetry. It's a sharp prosecution argument with a familiar sting. Supersymmetry remains beautiful, but is increasingly edging ever further away from testable ground. Once more, the defense team was forced to pivot. Their original alibi, that supersymmetry elegantly explained the Higgs mass, was quietly shelved. Now, a theory once operating on the fringes was called to the stand, an idea that came, at least in part, from Nima Akani Hamed. Akani Hamed was born in Houston, Texas, 10 days before Apollo 16 touched down on the lunar surface in 1972. His Iranian father, Jafar, worked on the program for NASA analyzing the moon's physical properties. After the Shah of Iran was overthrown in 1979, the family returned to the country, but it didn't last long. Ayatollah Khomeini quickly began closing universities, and Jafar was an outspoken critic. He was soon blacklisted. He'd be hanged if caught. Faced with little alternative, Jafar gave up his $50,000 life savings to people smugglers who were charged with ushering Jafar, Nima, and the rest of the family out of Iran on horseback. Except it didn't go to plan. 10-year-old Nima soon developed a fever and struggled to walk. Jafar ran for help. Nomads leapt to the family's aid, carrying the ailing Nima over the border on one of their horses. However, Nima's mother still feared he would die, and so desperate, she pointed up to the Milky Way overhead and promised her son a telescope if they made it out. She would later go on to say that she thinks her promise saved his life. And that boy in the mountains would grow up to become one of the most daring minds in modern physics, a theorist unafraid to question orthodoxy even when it means sacrificing beauty. Colleagues have called Akani Hamed a messiah, and indeed, according to physicist Raman Sundram, Nina's persuasiveness is hypnotic. A lot of people follow where he leads. In 2004, Akani Hamed, working alongside his former advisor Savas Dimopoulos, proposed a radical twist. What if supersymmetry wasn't beautiful and elegant at all? What if nature has carved it in two? This was split supersymmetry, where the symmetry is still real, but its effects are lopsided. The particles that help unify the forces and account for dark matter could still be light, but the particles that protect the Higgs from quantum instability might be unimaginably heavy, so heavy that the cancellation trick no longer works. In a sense, split supersymmetry was a plea bargain. The defense dropped one charge, that supersymmetry could explain the Higgs mass, in favor of doubling down on dark matter and force unification. Together, they still aligned with the deep structural architecture of string theory. Supersymmetry, even in this fractured form, was still playing by the rules. But, once again, there was yet another catch, and this was a costly one. By lifting the mass of the superpartners to extremely high energies far beyond the reach of the LHC or any foreseeable collider, split supersymmetry pays for its survival with testability. The heavier the particles become, the further into the fog of inaccessibility they recede. For the prosecution, this was the same old story. A theory that once promised to be falsifiable at LHC energy scales was now hiding its most distinctive particles on energy scales we may never probe. Experimental accountability was once again being quietly reclassified as optional. And yet, having said this, the theory is not entirely beyond reach. Split supersymmetry still predicts relatively light gauginos, the superpartners of the force carrier bosons. They could remain within the grasp of future accelerators or maybe even cosmological measurements. Split supersymmetry also retains viable dark matter candidates, and its predictions for force unification could, in principle, be cross-checked against future data on effects such as proton decay. And so while most particles may be lost to us, the theory's fingerprints haven't vanished entirely. And so, to the jury, the question becomes one of burden of proof. Does the theory's ability to evolve in light of new data count in its favor? Or is this yet another case of shifting the goalposts, a defense based on beauty once more slipping into evasion? The defense was out of conventional witnesses. What remained was the last resort. Another radical reimagining of the case itself. Beauty would return to the stand one final time, but in a form neither jury nor prosecution could have anticipated. Since we can never know anything for sure, it's simply not worth searching for certainty, but it is well worth searching for truth. Thunder cracks as the swirling sea toys with a shipwrecked sailor. Exhausted, he closes his eyes for what seems like the final time. Yet the storm clears and the ocean calms. The gentle waves then deliver the sailor to the safety of a sandy beach. As the sailor wakes, he takes in his new surroundings, a forest of trees buckling under the weight of plentiful fruit, a pool of fresh water, a sturdy shelter long abandoned. The castaway is astonished. Of all the places he could have washed up, why here? He sits on the warm sand, marveling at his luck. Yet some would say he wasn't really lucky at all. Indeed, the question of why here can only be asked on an island where survival was possible. After all, the dead could not reflect on their fate. Within physics, this logic is known as the Anthropic Principle. And in the early 2000s, the defense would come to rely on it to justify their case. And one man above all others took up this cause, a man who had been part of the string theory trial since the very beginning, one of the trio of people who came up with the idea in the first place. The defense recalls Leonard Susskind to the stand. Susskind may have started out as the Bronx plumber's son, but he would become string theory's street fighter, arguably its most combative advocate in the face of all the hand grenades thrown in by the prosecution. And the Anthropic Principle would be his counterpunch. The controversial principle comes in two forms: weak and strong. The weak Anthropic Principle simply states that the universe must allow observers like us, otherwise we obviously wouldn't be here. Take for example the fact that the Earth is at just the right distance from the Sun to have liquid water. According to the weak Anthropic Principle, that's no coincidence. Indeed, were it not so, we wouldn't be here to notice it. If the Earth had formed at a different distance from the Sun, no one would be here to ask the question. Like the sailor, we marvel at having been washed ashore on a habitable island, but of course we could never have emerged on any of the countless barren rocks where survival is impossible. Similarly, if dark energy were more potent and the universe had expanded faster, galaxies could never have formed and stars like the Sun wouldn't have ignited. It's no surprise then that we observe an expansion rate compatible with life. However, the strong Anthropic Principle goes further, arguing that the universe is fine-tuned for life. In this case, the right conditions for observers to emerge aren't just allowed. Nature is compelled to produce them. The emergence of life not some serendipitous fluke, but inevitable. And so when it came to string theory's failings, Susskind used the strong Anthropic Principle to flip the script. To the prosecution, the vast landscape of 10 to the power of 500 possible universes had been a fatal flaw. The theory that was supposed to explain everything, in fact explaining nothing. But to Susskind, the seemingly endless string theory landscape explained exactly why we are here. Physicists had long noted that our existence is balanced on a beautiful but precarious knife edge. An orchestra of particles, each with precisely tuned masses and charges. Gravity is the conductor, keeping time with just the right amount of pull. Dark energy is the counter-melody, introducing just the right level of push. And so how, despite seemingly impossible odds, is the universe so perfectly fine-tuned for life? Because, said Susskind, it isn't the only one. If the string theory landscape represents an unfathomably large number of different universes, with the constants of physics varying in each, then in which of those myriad universes are we going to find ourselves? It's as though the landscape were a sprawling archipelago. Most of its islands are barren, storm-lashed rocks where no sailor could survive. But there are a few rare oases, places with the cosmic equivalent of fresh water, fruit and shelter. And just as the curious castaway could only wash up on one of those hospitable shores, so too can we only find ourselves in one of the universes where life is possible. By allying string theory with the strong Anthropic Principle, Susskind was turning the very feature the prosecution were calling an unmitigated disaster into a cornerstone of the defense. And he laid out his case in a 2003 paper entitled The Anthropic Landscape of String Theory. It was a move that enchanted some members of the jury while enraging the prosecution. Indeed, the defense was now claiming that string theory was the very reason the trial itself could even be convened. No string theory, no trial. By this logic, given that we find ourselves in a courtroom, the jury has to find in string theory's favor almost by default. Of course, the prosecution was quick to object to what they considered scandalous circular reasoning. To argue that a theory must be true, otherwise we would not be here to argue about it, wasn't evidence. It was yet more sleight of hand, beauty somehow masquerading as inevitability. And so to counter what they saw as an absurdity, the prosecution turned to a big hitter of their own. A man who would repeatedly and publicly clash with Susskind over his use of the anthropic principle to justify string theory. The court calls Lee Smolin to the stand. Like Susskind, Smolin is a New Yorker. His own path to physics top table was hardly conventional. He dropped out of high school due to boredom before talking his way into college. From the outset, Smolin was an outsider, willing to challenge the orthodox approach. And by the early 2000s, that challenge took aim squarely at Susskind. The two men clashed bitterly over string theory's growing reliance on the anthropic principle. At first it was private emails, then literary agent John Brockman intervened, staging a kind of intellectual knife fight on his website Edge. Each man would write one final statement, unseen by the other, until both were published. Smolin did not hold back. The anthropic principle, he wrote, was so vague that one can get any conclusion one wants. It cannot help us do science. A theory that could never be falsified, he argued, had no place in the courtroom of physics. It was little more than philosophical hearsay. To Smolin, invoking the sailor's good fortune was no explanation at all. It was survival bias, dressed up as science. And Susskind was equally cutting. Let's not put the cart before the horse, he warned. Science is the horse that pulls the cart of philosophy. What critics dismissed as unfalsifiable, he reframed as simply not yet testable. Then he twisted the knife. What people usually mean, he added, is that they themselves lack the imagination to see how to test the idea. Next came the alibi. Quarks, Susskind reminded the jury, were once derided as unobservable too. No one could isolate a single quark, so critics called the idea metaphysics. And yet quarks went on to become the bedrock of modern particle physics. Indeed, ironically, it was quarks that had killed Susskind's original hadronic string theory decades earlier. Now he summoned them back as corroborating evidence. The clash between Susskind and Smolin was more than a personal battle. It was the entire trial in miniature. Is string theory a bold but unfinished science, or an elaborate ruse hiding beneath a veil of beauty and inevitability? And so after decades of claims and counterclaims, the long-running trial had at last reached its final stage. It is time for the closing arguments. For the defense, the allure of string theory is simple. It is the only framework that has ever naturally united gravity with quantum theory without breaking the mathematics. Other contenders for a theory of everything exist, like Smolin's own loop quantum gravity, but none have been able to explain such a wide range of phenomena. And it's not like there hasn't been progress along the way. Supersymmetry, the Green-Schwarz mechanism, the various dualities, D-branes, the holographic principle. These aren't just beautiful mathematical concoctions. They've become important tools in other fields. From condensed matter and quantum information to black holes and nuclear physics. String theorists freely admit that many of their predictions are beyond the reach of current experiments, but one day that could change. The absence of evidence is not evidence of absence. Black holes, quarks, and even parity violation were once dismissed as absurd and fanciful. Now all three are mainstays of modern physics. And so is it really so hard to imagine that strings vibrating across multiple dimensions could one day join that list? Science often demands patience. Like the cathedrals of old, a good theory can take more than a human lifetime to build. Those who lay the first stones know they will never see the spire completed, But that doesn't diminish the importance of their contributions. And so in a sense, modern string theory, in the guise of multidimensional M-theory, is a blueprint and a scaffold, not a finished building. At its core, string theory has always been about beauty, the enchanting compass that has so often pointed physicists towards undiscovered truths, like fingerprints nature has left at the scene. The defense concludes with an air of defiance. If string theory is guilty of anything, it is only of being ahead of its time. But of course, the prosecution disagrees in the strongest possible terms. String theorists, they argue, have been blinded by beauty. For nearly 60 years, the theory has laboured on without a single shred of experimental evidence to support it. Searches for supersymmetry, for example, the most crucial aspect that saves string theory from falling apart into a slag heap of tachyons and no parity violation, continue to fail. And yet every time experiment refutes one aspect of string theory, it's seemingly put back together with an even more elaborate sticking plaster. For a theory that's supposed to be elegant and beautiful, it has metastasized into a monstrous chimera. Beauty has become only camouflage, concealing contradictions behind a veil of aesthetic appeal. A multitude of extra dimensions, Calabi-Yau manifolds, wrapped up M-branes, all of them necessary to save string theory's blushes, not one of them ever glimpsed in the real world. And ADS-CFT, which predicts a curvature of the universe that's the opposite of what we actually observe. But the most egregious overstep, the prosecution insists, is the string theory landscape. The use of the anthropic principle to invert the case in string theory's favour is the final abdication of science's duty to predict and have those predictions falsified through experiment. It is no longer physics as poetry, but physics as religion. A compass that points in 10 to the power of 500 different directions is no compass at all. And so, the gavel falls one final time as the jury retires to consider its verdict. After days of deliberation, they finally return to the courtroom. The foreman stands. The jury is hung, unable to reach a unanimous verdict. Some are dazzled by string theory's elegance. Others, however, think it claims too much and explains too little. The foreman notes that beauty has been both saviour and saboteur. It rescued string theory when evidence failed, but also lured it into existential cul-de-sacs that make it hard to support. The judge has little choice but to declare a mistrial. It is clear that the case cannot be resolved with the evidence currently before the court, and so the file is left open, pending the arrival of testimony only the universe can provide.